apply to this transition-free models and beyond.
Okay, thank you. And yeah, let me continue my lecture today. And so this is what I presented yesterday. So this is the outline of my entire lecture this week. And yesterday I introduced the notion of frustration-free systems. And then I took you through several different examples like a KRT model, Majumdar-Ghosh model, toric code, and so on. And then I showed a systematic construction for frustration-free models from given some known models. But yesterday I just showed you some recipe for constructing new models, but I didn't really show any demonstration. I didn't really demonstrate anything. But today I'm going to show you that you can really cook up a new frustration-free model from a known model, some given model. And this is what I'm going to talk about today. And tomorrow I will focus on something more related to dynamics, quantum dynamics. All right. And okay, so let me first recapitulate what I have shown, so far. And here's a setup so that your total Hamiltonian is made up of these small sub-Hamiltonian, little hj, and each hj satisfies this operator inequality. But this inequality just means the ground state energy of this small guy, hj, is ej upper naught, right? And then here's the definition of frustration-free system. And this Hamiltonian, which is a sum of hj, is said to be frustration-free if there exists a state psi such that hj psi equals ej upper naught psi for all j. I mean, this literally means, this psi minimizes each local Hamiltonian independently. So, and in other words, this state psi saturates Anderson's bound. I talked about Anderson's old paper yesterday, right? But you can actually set the ground state energy to be 0, and then if you do that, here's a universal form of the Hamiltonian. So the Hamiltonian is sum of the Lj dagger Lj, and because of this form, each term is positive semi-definite, so that sum of them is positive semi-definite as well. So this entire Hamiltonian is positive semi-definite. So this means if you find a zero energy state for this Hamiltonian, it is a ground state. And in general, you might have multiple ground states, and the ground state manifold is spanned by these states from psi 1 to psi n, and each of which satisfies this relation. All right. And then here's a recipe for constructing new models. And the first method I introduced yesterday was the conjugation, which was originally invented in the context of supersymmetric quantum mechanics by Witten. And this is a deformation of L operator, which I denote by Lj cubed. But this is nothing but a conjugation of Lj by this invertible operator M. And then this is the deformed Hamiltonian. This is the sum of the L tilde dagger L tilde. And by construction, you see the ground state manifold of a new Hamiltonian is spanned by these states. So, we need to modify this, original ground state by n this way, right? And then you can slightly generalize this idea by considering the sandwiching method. And here you can introduce positive definite operators, Cj, which means each Cj only has positive eigenvalues. And then you can further deform the Hamiltonian. And this new one is given by this. And you see you are sandwiching this Cj by L tilde dagger and L tilde. But this doesn't change the ground state manifold, so it remains the same, right? So they are the same. And by construction, you see this H nu and H. Original Hamiltonian have the same number of ground states. So this kind of deformation doesn't change the number of the ground states. All right. Okay. And I think yesterday he kept asking me questions about why frustration-free models are important, right? And so actually, so when it comes to summer school, I have some memory about the Jewish summer school in 2006, which I attended when I was a PhD student. So it was more than almost 20 years ago. And so actually the list of lecturers at that summer school was impressive. You see, the list includes Ian Affleck, Holden, and Kitaev, and Sawatsky, and late Suchanjan. And so actually I don't quite remember anything about the lectures, but one thing I still quite remember was a conversation between Alexei Kitaev and George Sawatsky during dinner, one day during dinner. And actually, Alexei Kitaev was giving a series of lectures about exactly solvable models like toric code and Kitaev honeycomb model and so on. And yeah, I learned a lot about those exactly solvable models from his lectures. But the conversation was actually really interesting. I was a poor PhD student, and I hesitated to get into the conversation. But they were like, George Sawatsky was like, Alexei's talk about Kitaev honeycomb model was interesting. But his question was, does it have anything to do with real materials? Or something like that. So yeah, maybe I might have cooked up some story, but anyway. So, and then the answer, Kitaev's answer was, oh, maybe I must disappoint you, or something like that. But some years later, people started talking about the realization of the Kitaev honeycomb model using real materials like iridium oxides and some other materials, right? This was first discussed by George Jacqueri and others in this paper. So maybe this might give you some answer to your question yesterday, right? So maybe sometime those artificial model could find some applications in real materials. And yeah, okay, that's my hope. And okay, so here's the outline of my lecture today. And today I'm going to mostly focus on Kitaev chain, both interacting and non-interacting cases. But before that, I will introduce the notion of duality in both classical and quantum Ising models. And then in the second part, I will introduce the non-interacting Kitaev chain, which is just a free fermion model, right? And then in the third part, I will introduce frustration-free Kitaev chain, which can include some kind of interaction between electrons. And in the final part, I will introduce some generalization of these interacting Kitaev chains, which are frustration-free quantum Potts chains. Okay. So let me start with something quite simple. That is the 2D classical Ising model. And I think everybody knows what the classical Ising model is, right? So this is just elementary stuff in, classical stuff, right? But just in case, so let me just define the model. And this is the definition of the model. And this ball sigma is a set of spin configurations, and each spin sigma, this sigma I takes value either +1 or -1, and spins are leading on this square lattice. I'm focusing on the 2D Ising model here. And this is the Hamiltonian of the Ising model, but this is, we are dealing with just a classical model. This Hamiltonian is just the, energy, right? And the energy is determined by the spin configuration sigma. So this is a function in sigma, and you have this sum of the nearest neighbor interaction, and here I'm considering the ferromagnetic case, so J is positive. So meaning, if the spins are taking the same value on some bond, then it minimizes the energy. But if the spins are opposite, then you get some higher energy, right? And this is the definition of the partition function. So it's the sum over these Boltzmann weights. And this 2D classical Ising model was solved by Onsager in the 40s. But the way he solved the model was rather involved because he used something complicated, which is called the Onsager algebra. But later on, Kaufman found a bit better way to solve it. So she found the Majorana-Fermion trick to solve the 2D Ising model. So solving the model is rather involved, but the physics of the classical Ising model is rather simple, and you can just consider two extreme limits. So at zero temperature, which corresponds to beta equals infinity, you only have ground states at zero temperature, and the ground states here are all up state or all down states, so they appear with the same probability 1/2. But at infinite temperature corresponding to beta equals 0, all states occur with equal probability. So this is the paramagnetic state. And this is a schematic phase diagram of the model as a function of beta inverse temperature. And so, in these two extreme limits, the physics is simple. But you can expect critical point between these two phases, right? In the paramagnetic phase, the order parameter, which is the magnetization, is 0, but in the ferromagnetic phase, it's non-zero, right? But in between, there must be a critical point, beta C, right? And of course, the 2D Ising model is solvable. So once you get the free energy from the partition function, you can really get the exact location of the beta C. But as I said, the exact solution is rather involved. But there is a shortcut to get this value of beta C using the duality. And that's what people like Kramers and Wannier came up with in this paper. And okay, so this is again the partition function of the classical Ising model. And for simplicity, let me denote by k this beta j. And you can derive this partition function this way, and this ij, this guy runs over all the nearest neighbor bonds, right? And here, this useful identity comes into play. So you see this sigma state only +1 or -1, so the square of sigma I, sigma j is just ±1, right? And then you can derive this exponential of k sigma I sigma j this way. So you can rewrite it using the cos and the hyperbolic tangent. And then if you plug this in here, then you get this different expression for the partition function, right? And then you can use this kind of identity. So here, n runs from 0 to 4. When this n integer is even, then you get 2. If this is odd, you get 0. So this is an exact identity. And then you can just use this relation to simplify this expression. And then you get this expression. And here, this P is a configuration of loops. And so let me explain what it is. And so these are examples of loop configurations. And so in this graph, you don't have any loop. And this LOP is the total length of loops So here, because we don't have any loop, so this LOP is just 0. But in this configuration, you see you have this little loop here, right? And for this configuration, LOP is 4. And for this, you have LP, which is 8. And in this configuration, you have two kinds of loops, and some of the loop length 12 in this case. And you have many different loop configurations, but you need to sum of these configurations here. But so this is not so useful now, but now you can change the variables from the original spins to dual spins. And now, yeah, dual variables live in these faces of squares, and then I label dual lattice size by a equal 1, 2, 3, blah, blah, blah. And yeah, this is the set of dual spins, which I denote by this old mu, and mu equal minus 1 if this face is inside the loop, and this is plus 1 if it's outside the loop. And of course, so whether it's inside or outside is a bit subtle, but maybe you can just fix the boundary spins to plus 1 or something like that. And this way you can avoid some subtlety. And this way you can introduce dual spin variables. And in terms of this new variables, now you can derive the partition function this way. And here, this LOP is what I introduced in the previous page. And you can derive this LOP in terms of these dual spin variables. And here, this AB runs over all the nearest points in the dual lines. And if you plug this in here, then you get this expression for the partition function. And this k tilde is related to the original k via this relation. But if you ignore this prefactor, this partition function looks almost the same as the partition function of the original one. Yeah, yes.
Could you repeat why we consider these loops?
Sorry.
Could you repeat why we consider closed loops?
Closed loops. Okay, yeah. Good question. So here, from here to there, I use this identity, and this is 0 when n equals 0, n equals 1 or 3. But n equals 1 means, for instance, in this loop configuration, when n equals 1, you have this kind of configuration. Something like this, or anyway, I mean, because of this identity, these configurations are restricted to the graph such that each loop configuration only contains closed loop, or more precisely, at each vertex only even number of vertices, even number of these lines are emanating. I mean, that came from this identity. I mean, this kind of graph is not allowed in this expansion because of this identity. Is that clear?
Because then n is not.
Okay, yeah, maybe I should have said this way. Yeah, suppose you have site ijk like this, and then you know, if you consider the product of this guy and this guy, and consider the sum over sigma j here. And then you have 4 terms, right, if you expand this product. But then, yeah, maybe I can write this way. 1 plus this guy. But if you take us sum over sigma j here, this will vanish, right? Sigma j is plus minus 1. And this also vanishes. And this one, this guy corresponds to this empty line. And this guy corresponds to, I mean here, because this is 1, you get zero value from this guy, right? And this guy corresponds to this field lines. So this is the root. I mean, so I did this locally, but you can do it from any other sites.
So what you represent with the line is actually
Okay, yeah, good question. So here, line just means, for each line, I assign this hyperbolic tangent k. So here, we don't have lines, right? So field line, we only have empty lines. So this is just a 1 times 1. And here we have a tangent k, so that's why we have this square of hybrid tangent k. Does that make sense? Okay, thank you. So, okay, let's come back to this partition function in terms of use. And you see this part is almost like a partition function in terms of original spin, but not quite because this coupling is different. But, if you assume the presence of a single critical temperature, then you can get the critical value of K. Because, if the free energy is singular at some k, and then it's also singular at this k2 because of this duality relation. But if they are different, then this means you have 2 critical points. So, but that's contradicting with this assumption, right? So if you assume only a single critical point, then you get this condition, k equal k2, k2. And then if you solve this condition, then you get the critical temperature delta C, which is this value. And if you set J to 1, then this is 0.44. Okay, so this is the critical point of the 2D classical Ising model. And as you know, the duality in the classical problem is a little bit complicated because we have to deal with these, hyperbolic functions, and they are a little bit complicated. But duality in the quantum case is rather simple. So now let's move on to the duality in the quantum Ising chain. And these are your familiar 2x2 power matrices. And as I explained to you yesterday, you can express the spin operator in the many-body case, like this kind of tensor product. And then this is the Hamiltonian of the quantum Ising model. And you have this interaction term and the magnetic field term. And this is a phase diagram of the model. And if the magnetic field is much weaker than the interaction strength, the ground states are ordered states. So, when you set H to 0, then you get the O plus state or O minus state. And here, plus minus states are basis states for sigma x. But if you consider the other limit, where H is much larger than J, and then you are in a paramagnetic phase where spins are pointing or up direction. And the critical point occurs at H equal 1, and it's described by the central charge 1/2 CFT. But again, you can pin down this critical point using the duality. And here's the quantum version of the duality. And you can think of duality as a unitary transformation. And this U and V are unitary transformations defined by like this. And you can check that by sandwiching sigma z by uv, you get this sigma jx, sigma j transform x. And if you sandwich this guy by uv and uv dagger, then you get sigma j transform z. So this unitary transformation changes the roles of magnetic field and the interaction term. And then if you sandwich the original Hamiltonian by uv and uv dagger, then you get this Hamiltonian. And here the roles of J and H are interchanged. But because this is a unitary transformation, they must have the same spectrum, right? But here I'm a bit cheating because this kind of unitary transformation gives rise to some boundary terms, but let's ignore it. And if you ignore it, then you can get this kind of relation. And again, if you assume the presence of a single gapless state in this model, then it should be at H equal J. This is the critical point at which the model is gapless. So, okay. Yeah, I'm going to discuss how this is related to the topology of the Kitaev chain. So, any questions so far? Okay, now let's move on to the second group, and I'm going to introduce the non-interacting Kitaev chain, and I will introduce Majorana fermion expressions, and then I will argue there are two different phases in these models. And you can see the difference between these two phases by considering the topological invariant. And topological invariant is defined in momentum space, K space, but you can find the implication in real space. That is the presence of edge states. Okay, so now let me introduce Majorana fermions, or more precisely, lattice Majorana fermions. And this is the Majorana operator gamma J, and these are defining relations of Majorana fermions. And they are their own Hermitian conjugates, so this relation holds, and they intercommute with each other. And you can define the fermion parity by the product of these gamma operators this way. And then, actually, you can find the connection to spins. So, yesterday and so far, I've been talking about mostly spin models, but you can express these Majorana fermions in terms of the spin operators. And here is one version of Jordan-Wegener transformation. There are many, equivalent, but looking different expressions. This is one choice. And in terms of spins, this fermion parity looks like this. And yeah, maybe let me show you why this is correct. Yeah, just for simplicity, let's consider the small system L equal 2. And for this case, this gamma 1 is just sigma 1x. Gamma 2 is sigma 1y, and gamma 3 is sigma 1z, sigma 1m, sigma 2x, and gamma 4 is sigma 1z, sigma 3y. And gamma 1 and gamma 2 anti-commute with each other because these Pauli operators are anti-commute, right? And this gamma 1 and gamma 3 also anti-commute because this sigma x and sigma z anti-commute. And this way you can show that these are all mutually anti-commuting. And because any of these sigma a squared equal 1 for any a, so you see each guy squares to 1. So this way you can check that this duration holds, right? And if you consider the product of them, then gamma 1, gamma 2 is sigma 1x, sigma 1y, but this is I times sigma 1z. And similarly, if you consider the product of gamma 3 and gamma 4, then sigma 1z squared is 1. So we just get sigma 2x, sigma, sorry, this is my mistake, so sigma 2y. And this is I times sigma 2z. So if you, multiply them, then you get I squared sigma 1z, sigma 2z. And this way you can prove that this duration holds, right? And okay, now let me introduce spinless fermions in terms of Majorana fermions. And you can construct ordinary complex fermions out of these Majorana fermions. And these are the definitions of annihilation and creation operators of spinless fermions. And they obey these standard canonical anti-commutation durations. But you might think, these spinless fermions are rather artificial because, electrons must have spin degrees of freedom, right? But there is some big scale cues here. So let's discuss how you can get rid of these spin degrees of freedom. And there are a lot of discussions in the literature, but let me just follow these references. And let's consider this wire system. And here you have a 1D wire here in a magnetic field. And there is also a spin-orbit interaction, which you can think of as some fictitious magnetic field in this direction. And I'm not considering a continuous system. So electrons are moving in this 1D continuous system, and if you don't have magnetic field or spin-orbit interaction, then you just have this quadratic band structure here, right? And this case just momentum. And because of the time reversal symmetry, these two bands are degenerate. But if you turn on the spin-orbit interaction, then these bands will split like this. But you still have a degeneracy at k equals 0, because the k equals 0 is special in that it has a time reversal invariant. It's a time reversal invariant point. So this degeneracy is protected by time reversal symmetry. It's just a Cramer's degeneracy. But you can spread this degeneracy by adding a magnetic field, because magnetic field breaks time reversal symmetry, right? And if you turn on this B, then you get this splitting, so you have an upper and lower bands. And then low energy, you can just focus on these two Fermi surfaces, Fermi points. And low energy, you can derive effective Hamiltonian, which is essentially described by spinless fermions. And this way, you can justify the use of spinless fermions in this kind of system. But okay, now let me go back to just the radish models. And here's the Majorana expression for the Ising model. So as I said, you can express Majorana fermions in terms of spins. But you can do the other way around. You can express spin operators in terms of Majorana fermions. And if you do that, you get this Majorana expression for the Ising model. And this is nothing but the Kitaev chain Hamiltonian, which was studied in his papers. And in this language, the duality I discussed earlier just means the translation by one Majorana side. So, in this system, you have a translational symmetry by, by two sides. I mean, if you shift the system by two sides, then you recover the same Hamiltonian. But if you just translate this Hamiltonian by one Majorana side, then the rows of J and H are swapped, right? And so this is exactly the same as the duality transformation. And the self-duality at the critical point means emergent translational symmetry at J equal H. Because at J equal H, you have additional symmetry, right? I mean, this Hamiltonian is invariant and one side shift. And you can also express this Ising Hamiltonian in terms of spinless fermions. And here's the Hamiltonian in terms of C and C dagger. And the first term represents the nearest neighbor hopping, and the hopping term between these neighboring sides. And the second term is the pairing term, interside pairing term. And the last term represents the chemical potential. And this H Ising and H naught are identical when you identify J with W and this H with mu over 2. So now let's discuss the phases of Kitaev chain. And this is the Majorana expression for the Hamiltonian. And now, okay, so let me first consider the trivial case where this W is much smaller than mu. In which case, the second term dominates the Hamiltonian, right? And in terms of spinrich fermions, this H naught looks like this. So you only have a chemical potential term, right? And if mu is quite large, then the ground state is the state in which each side is filled by one fermion. I mean, the fully filled state is the ground state of this model. But let's consider the other limits, the other extreme limit, where W is much larger than mu. In which case, the first term dominates the Hamiltonian, right? In this case, in terms of Majorana fermions, you have these intersite couplings. But you see here, this J index runs from 1 to L minus 1. So, in this Hamiltonian, you don't have gamma 1 and gamma 2L. They don't appear in this Hamiltonian. But that means if you construct this new fermion operator in terms of gamma 1 and gamma 2L, this guy and the F dagger commute with the Hamiltonian. So that means the presence or absence of this new fermion corresponds to the degeneracy in the ground state. in other words, if this 0 ket is a ground state of the model, then this 1 ket, which is f dagger 0, is another ground state. And this kind of local mode exists as long as W is larger than mu. And this is a kind of a real space picture of the two phases, trivial and topological phases. And in the topological phase, you have this non-local edge mode. But now let's discuss the, bulk topological invariant. And if you consider a model with periodic boundary condition, you can easily solve it because you have translational symmetry. You can just Fourier transform the Hamiltonian, right? And this psi of k is this psi k and psi dagger minus k are Fourier transforms of C and C dagger, which I discussed, right? And here this calligraphic H of k is 2 by 2 matrix. It's Hermitian, so you can parameterize this 2 by 2 matrix by this Pauli matrices. And this is just a vector, 3-component vector. And there is a symmetry in this Hamiltonian. And actually, you can prove that the components of dx and dy flips the sign when you flip the sign of momentum. But the z of k doesn't change when you flip the sign of the momentum. And this is the symmetry of this 2 by 2 Hamiltonian. And then let me introduce n vector, which is a normalized version of this d of k. And you have a non-zero gap in this system when this d vector is non-zero. And okay, here comes the topological number. And as I said, this Hamiltonian has this symmetry. And here, this momentum k equals 0 and pi are special because, for these two momenta, k and minus k are equivalent, right? And because of this symmetry, k equals 0, this d vector must point to the north pole or south pole. It should be proportional to this unit vector in the z direction. And that is also true at k equals pi. So there is some constraint for this vector at k equals 0 and pi. And here, S naught and S pi are +1 or -1 because I normalize this vector. And there are two possibilities when you vary the momentum k from 0 to pi. And in this case, if you vary k from 0 to pi, then this n vector is coming back to the north pole again. But in this case, if you vary k from 0 to pi, then you are going from the north pole to south pole. And you cannot diabatically connect these two cases without closing the gap. So these two cases are topologically different. And there must be a critical point between these two cases. And okay, so this is the momentum space picture, but now let's discuss the real space picture. So let's discuss what the implication of topological invariant is. And here you have a Kitaev chain in the topological phase on the right, and you have trivial phase on the left. And this is the real space system, but you can think of this axis as some parameter. And as I said, you cannot connect trivial and topological phases without closing the gap. And this means between these two systems, you must have a gapless node at the interface, right? And this interface mode, surface mode, is robust against some small, tiny deformation of the Hamiltonian. And here's a more precise definition of Majorana edge zero modes. In Majorana edge zero modes, gamma are such that Hermitian and it commutes with the Hamiltonian and it anti-commutes with the fermion parity and it's localized near the edges and it's normalizable. And actually this definition also works for the interacting system, but you may just consider non-interacting Hamiltonian H0 for the moment. And this is a schematic picture of the spectrum, and by acting with gamma, you can get degenerate eigenstates with different fermion parity. And you can actually construct this kind of edge mode explicitly for the non-interacting case. And here I'm considering a model with disorder, meaning this hopping amplitude depends on the this position site.
I have a question.
Sure, sure.
Does it play a role that one Majorana is not a physical C fermion?
I mean, C fermion shouldn't be Majorana, right? Because C and C dagger
Yes.
are different.
Exactly.
But if you consider something like C plus C dagger or C minus C dagger over I, they're Hermitian.
But when does it play a role? So if we act with the Majorana H0 on the ground state, then this Majorana H0 does not itself correspond to something physical like a C fermion. When does this play a role? So when do we have to consider a combination that isn't actually known?
Yeah, that's a good question, actually. So what I said earlier was, if this zero K is a ground state, and then you get another ground state by acting with F dagger on this zero. But this F dagger is a sum of gamma 1 and something like that. Right? But actually, I don't think I have time to work it out now, but you can also show this kind of relation. I mean, this is one. This is proportional to 1. Something like this. Yeah, actually I forgot, but there is an easy way to understand why this is true.
Because you can express F via, we can express gammas via F and F dagger, and F always acts trivially on 0, so you always get 1.
Yeah, you're right. Yeah, right. So the important point here is that this n is an eigenstate of, this 0K is an eigenstate of this n, which is F dagger F, right? We have to take this to be an eigenstate of n. That's important. I mean, if you consider some mixture of 0 and 1, and then this kind of argument fails. Okay, thank you. So, it's okay? Okay, anyway, so here I'm considering an inhomogeneous version of the model where the toppings are spatially dependent. But even in this case, you can construct Majorana zero mode, which looks like this. So, I mean, if mu1 is much smaller than w1, this is smaller than 1, and I mean, if they satisfy certain duration, then these prefactors decay with position. And if that's the case, then this gamma here is normalizable. And you can check that this guy with the Hamilton, if you ignore the other boundary, if you consider semi-infinite system, this commutes with the Hamilton. Okay, now let's move on to the third part, and I will introduce the frustration-free Kitaev chain. And I will first consider the decoupling limit of the non-interacting case. And because it's just non-interacting model, you can easily solve it. And then if you apply the Witten's conjugation and sandwiching method, which I introduced yesterday, then you can construct interacting version of the Kitaev chain, for which you can get ground state exactly and explicitly. And for this frustration-Kitaev chain, frustration-free Kitaev chain, you can prove the existence of a spectral gap. You can prove an energy gap above the ground state. And this work was done in cooperation with this Masahiro Takahashi and Dave Schurz and his student Yuri and Udas. So now, let me first discuss the decoupling limit of the Kitaev chain. And so, you know, in the original model, you have a W and mu term, but here I only take a W term. And you can factorize this local term this way. This is the product of these two guys. And let me denote by AJ dagger, this guy, and AJ is this guy. And in terms of spinless fermions, AJ looks like this. So this is the sum of these four operators. And then you can show that this coherent state, psi plus minus, is a ground state of this H node. And it's actually annihilated by OAJ. And okay, let me prove it. So AJ is a sum of four operators which you can organize in this fashion. So Cj minus Cj dagger minus Cj plus 1 plus Cj plus 1 dagger. And what I want to prove now is this equation Cj minus Cj dagger psi plus minus equal this. You know, if this is the case, you can show that AJ annihilates this psi plus minus this. And here's the definition of psi plus minus, which is E C1 dagger, E C2 dagger, blah blah blah, CF dagger, vacuum. And vacuum is just an empty vacuum state. And because, you know, this C dagger squares to 0, they are nilpotent operator, you can also write it this way. Sorry, I mean plus minus here. So 1 plus minus C1 dagger, 1 plus minus C2 dagger, blah 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 blah, plus minus CF dagger. Right? And let me first compute the left-hand side of this equation. And, you know, if you commute this guy with e to the plus minus C1 dagger, then you will flip these signs because, I mean, if j is not equal to 1, they anti-commute with C1 dagger. So you can take this Cj minus Cj dagger all the way to J's and so on. So if you compute this, you get minus plus C1 dagger, blah, blah, blah. And then you have 1 plus minus CJ dagger. And then like this. And now let's compute this part. And then you get CJ and minus CJ dagger plus minus CJ dagger. And because CJ dagger squared is 0, you just get it. This one, right? And then if you use the anti-commutation relation between C and C dagger, you can rewrite it this way: 1 minus CJ dagger CJ. And then you can take this CJ all the way to the right, because they are just this guy just anti-commute with these guys. But in any case, you can take this guy all the way to the right, and then you get just 0 because CJ another is vacuum. And similarly, this part just gives you 0. And this way, you can rewrite it as plus minus 1 minus CJ dagger, and the rest is the same. But this is nothing but plus minus 1 minus plus CJ dagger. And this is the same as the plus minus e to the minus plus CJ dagger. So to summarize, if you act with CJ minus CJ dagger on side plus minus, and then what you get is this. E to the minus plus CJ minus 1 dagger, e to the minus plus CJ dagger. Yeah. You see that these signs are going up to side J, but the rest is remains the same. And then you can do the similar computation for CJ plus 1 plus CJ plus 1 dagger side plus 1. Yeah, I don't want to do the computation because this is more or less the same as this kind of computation. So let me just write the result. And actually, this sign difference here is quite important. Because of this difference, you get the same expression. So you see, they are the same, right? They get the same answer, so they will cancel out. And this way you can prove that psi plus minus are zero energy ground state of H naught. And because H naught is positive semi-definite, if you find a zero energy state, then it's a ground state, right? But there is a problem here because these psi plus minus are not eigenstates of the fermion parity, you have to take some proper combination to make it an eigenstate of -1 to the f. And you can do that. For instance, for two sides, if you take this positive combination of psi plus and psi minus, it looks like this. This is the linear combination of vacuum and fluid fused sides, fluid fused state, and if you consider negative combination of them, then you get this one particle state. And they are eigenstates of -1 to the f. And you can keep on, and for L equals 3 sides, this is the ground state belongs to the even fermion parity sector, and it's an equal weight superposition of these states with even fermion parity, and this is a ground state in the odd fermion parity sector. I mean, they are graphical expressions, but you can, in principle, write them out in terms of C dagger and C operators. And so, I mean, proving this is was not so easy, but there is an obvious way to convince you that this is a ground state of the model. So, as I said, you can also express the Hamiltonian in terms of spins, right? And this is the spin model Hamiltonian corresponding to the Majorana Hamiltonian in the previous page. And this is just the classical model because this only involves the sigma x operators. And you can factorize this local Hamiltonian this way. So Hj is Lj dagger Lj, and this Lj is just this guy. So sigma j x minus sigma j plus 1 x over square root 2. And you see this is just diagonal in the basis in which sigma x is diagonal. So this plus minus can diagonalizes sigma x. And here's the ground state of the model. So you have two ground states. You see, these product states are zero energy ground states of this classical model. And there are no other ground states. And this is the ground states in terms of up and down x. And if you identify up with empty state and down with field state, and this is equivalent to the fermionic ground state in the previous page, this guy. Okay, now let's consider the Witten's conjugation of the model. So, and here's an invertible operator n, which is defined by this number operator n. And an inverse looks like this. And now you can consider the conjugation of C and C dagger by n. And if this is correct, then you get the conjugation of A this way. And let me prove it. So this M operator looks complicated, but this is just a product of some constant cross number operator. And so what I want to prove now is this is just one. But this is easy to see because this is just a product of J from 1 to L. And the point here is, these are just diagonal operators, so they are mutually commuting. The order here doesn't matter, so you just need to compute this single guy. And you get 1 plus alpha minus 1 and j, alpha inverse minus 1 and j, plus this. But this, nj squared is just nj, because nj squared is cj dagger cj, cj dagger cj. But using the anti-commutation relation between c and c dagger, you get 1 minus cj dagger cj. But because c squared is minus, sorry, c squared is 0, you just get cj dagger cj, which is nothing but nj. So you can rewrite it as nj. And then here you only have 1 plus something linear in n. So the coefficient is alpha minus 1 plus alpha inverse minus 1 plus this product. So 1 plus alpha plus minus. Sorry. Nj. Yeah, but if you add them up, then you just get 0. So it turns out that this is just a product of 1, so you just get 1. And you can also show that n inverse n is 1. So this n inverse satisfies these iterations. And okay, next let me show that n sends Cj to alpha inverse Cj. And here, left hand side is, I mean, these guys mostly commute with Cj, so you just get 1 plus alpha minus 1 nj right? I mean, this number operator and Cj have some non-trivial commutation duration. But here, the product of them is just trivial because you have Cj squared here, right? So you just have Cj 1 plus nj. And this is Cj plus alpha inverse minus 1 Cj nj, but the definition of nj is Cj dagger Cj. And then you can use the anti-commutation relation again. And then get Cj plus alpha inverse minus 1 Cj. But this 1 and minus 1 here cancel out, and you get alpha inverse Cj. You can do something similar for the C dagger and get this relation. So that means if you sandwich Aj by M and M inverse, then you get this complicated combination of those 4 operators. But in any case, for this a tilde, you can get a new ground state. And now you can use this relation. So this vacuum state is invariant under M. So if you act with M on the psi plus minus in the previous case, then you get this new ground state. So here you have these coefficients are modified from 1 to alpha this way. So this is a one parameter deformation of the decoupling limit of the Kitaev chain. And for L equals 3, these are the ground states, two ground states. And previously you only have coefficient 1 everywhere, but here you have these powers of alpha, and the power counts the number of fermions. Here you have two field size, so that's why you have 2 here. Yeah, something like this. And now let me write out the Hamiltonian, which is the sum of A tilde dagger A tilde. And if you compute this one, and then you get this local Hamiltonian H J tilde, which looks like this. So you have a Hawking term and a pairing term and this chemical potential term plus some number constant. But they are not independent to each other. And actually, there is a constraint here. So the delta over T and mu over T are written like this. So, we only have one parameter, alpha, so there must be some constraint. And they satisfy this relation. And actually, it turns out that this condition is exactly the same as the Barocci-McCoy circle discussed in the context of spin model. And you can actually read off the phase diagram of the Kitaev chain from that of the XY spin chain. And so this is the phase diagram as a function of delta over T and mu over 2T. And in this region, the model is topological, and outside is trivial. And this Barocci-McCoy circle corresponds to this semicircle like this. And on this circle, you have a decoupling limit, alpha equal 1. And on this, what they found for the spin model was on this circle, the ground state factorizes like this. So, I mean, the model is solvable because it's a free fermion model, but it doesn't mean that the ground state looks simple. But somehow, on this circle, the ground state is extremely simple. This is just the product state in the spin language. But in the fermion language, it's a bit more complicated because we have to preserve the fermion parity symmetry. But in any case, this is just a non-interacting model. So even if you don't know anything about Witten's conjugation, you can just solve it by Fourier transform. But now let's consider an interacting case. And you can make it interacting by sandwiching something between A dagger and A here. And this Cj can be anything as long as it's Hermitian and positive definite. But here's my choice. So this Cj is a sum of projection operators, and this P, E, and PO act on side J and J plus 1. And this PE is a projection to even fermion parity subspace, and this PO is a projection to odd fermion parity subspace. And this alpha 1 and alpha 2 have to be positive, otherwise, this can be, negative definite. And okay, this is the explicit Hamiltonian. So if you plug this in here, then you get these terms. And so up to here, it's just a non-interacting Hamiltonian. But now, in the last part, I have an interaction term. And this interaction term looks like this in terms of Majorana fermions. And again, we only have one parameter alpha, so they are not totally independent. And these, T, delta, mu, and U, interaction strengths, they must satisfy this condition. And under this condition, the model is solvable, and you can write down the ground states. And so actually people have studied the phase diagram interacting type chain. I mean, let's just consider more general case, which is not necessarily solvable. And there are several papers about it. But okay, let's consider the simple case where hopping and pairing are the same. And actually, in this case, the model is equivalent to the quantum version of the ANNI model. I mean, this is like a quantum eigenchain with next nearest neighbor interaction. And here's a schematic phase diagram for this case. And here horizontal axis u over t and the vertical axis mu over t. And the solvable case corresponds to this blue line. And this is written like this. So on this line, mu is this function of u. And along this line, the exact ground state looks like this. So it's a fermionic coherent state. And this line goes to mu equals 4u in the infinite u limit. So this approach is to mu equals 4u. And you see this solvable case falls into the center of topological phase. And this u equals 0 mu equals 0 corresponds to the decoupling limit of the Kitaev chain, non-interacting Kitaev chain. And so let me also write down the spin chain expression of the Hamiltonian. And if you do this Jordan-Wigner transformation, you can rewrite the Hamiltonian in terms of spin operators, right? And if you do that, then you get this spin Hamiltonian. And here you have XX interaction, YY interaction, ZZ interaction, and this magnetic field term. And if you don't have this magnetic field, this model is integrable. But if you have this term, then it's not integrable. Nevertheless, these parameters, Jx, Jy, and Jz, and B satisfy this condition, then it's frustration-free, which means you can write down the ground state explicitly. And it turns out that this was already found by those people, Hosho, Emery, and others. So what I found was actually just a fermionic rephrasing of what had been known already. Okay. So, but let me finally add something new. So far I've been just reproducing known results. So, okay, now let me prove that there is a spectral gap above the ground states in the interacting case. And in the non-interacting case, because you can just easily diagonalize the Hamiltonian by Fourier transform, you can easily prove the presence of a gap. And the gap is basically just a band gap, right? But in the interacting case, it's quite non-trivial because the band theory doesn't work now. So, but you can prove the gap for the frustration-free case. And here I want to use this mathematical theorem called the minimax theorem or minimax principle. So let me explain what it is. Okay, so here's the statement. So let A and B be two Hermitian matrices, and the small ai and small bi be the eigenvalues of A and B, respectively. And I assume this increasing order of A and B. And if A is greater than or equal to B, then we have this inequality. And this is trivial for I equal 1. For the ground state, this just means the variational principle. But the important point here is that it also holds for excited states. And now you can utilize this kind of theorem here, and you can, this is the Hamiltonian of the interacting Kitaev chain at the frustration-free point, and this alpha 1, alpha 2 satisfy this inequality. And as I said, these are projections to even and odd parity sectors, so some of them must be 1. And you can rewrite this part two different ways. in the first expression, I only have P, but the second one, I only have PO. And because alpha 1 minus alpha 2 is non-negative, this guy is larger than alpha 2, and but it's smaller than alpha 1. So you get this operator inequality for this interacting Hamiltonian. So interestingly, you can bound the interacting Hamiltonian by non-interacting Hamiltonians from the bottom and from the top. And so, and this, let's denote nth eigenenergy of the non-interacting Hamiltonian by En upper norm. And actually, we set the ground state energy to 0, so the first and second eigenenergies are 0. And because H and H0 tilde share the same ground state, so the gap of the interacting model is bounded by this inequality. So this E30 is just the third energy of the non-interacting model, so it's easy to compute. So this way you can bound the spectral gap of interacting model by the spectral gaps of non-interacting model. So for the non-interacting model, you can easily compute it. And I think it's too technical, so let me skip it. But anyway, so by the singular value decomposition of the Hawking PERT, you can get the spectral gap of the non-interacting model. And then you can prove that there is a non-zero gap above the ground space in the interacting model. And you can also write down the expressive expression for the H loss for the non-interacting model. Let me skip it. And yeah, we also studied a little bit more complicated model in which the chemical potential is varying in space, so it's staggered. But even if you make it staggered under some conditions, the model is frustration-free, and you can also have the interaction. They must satisfy some condition. The model is not solvable in general, but under certain condition, it's frustration-free. And that's what we studied in this paper. And okay, in the last, let's say 7 minutes, let's discuss the frustration-free quantum pulse chain. And this was done with, again, Dirk and his student, Yuri and Brutus. And actually, he read physics, but he's actually kind of famous because it's from Wikipedia, but Yuri was a previous champion of javelin in the Netherlands. So yeah, you can find him on Wikipedia. And anyway, so we studied the frustration-free version of the quantum pulse chain. So, okay, let me explain what it is. And okay, so here sigma and tau are so-called shift and block matrices, and here this tau I is an eigenstate of tau, but sigma changes this index I, from I to I minus 1. And this n is some integer, 2, 3, 4, and so on. And here's the Hamiltonian of the Potts chain, and you have this Potts interaction term and this magnetic field term. And the duality here means the swap between tau and sigma, that is sigma. And you can actually express this Hamiltonian in terms of power fermions, and this was done by Fradkin and Kadanoff in this paper. And this is the Hamiltonian in terms of power fermions, and you see if J and H are the same, and then you have an additional emergent translational symmetry by one power fermion site. And it actually corresponds to the gap rest point. And the model is critical when n equals, this n is 2, 3, 4, but it's at the first order transition point when n is greater than 4. But, okay, so the model is a bit complicated, but let's consider the classical case where h is 0. And in this case, because it's classical, it's easy to solve. And here's the factorization of the local Hamiltonian, and this Hj can be written like this, and this Lj is sigma j minus sigma j plus 1. And this classical Hamiltonian is diagonal in the basis in which sigma is diagonal. And this sigma ak is basis diagonalizing sigma, and this is the sum of linear combination of these three states, and A runs from 0 to 2, and the ground state looks like this, so it's just a product space in this basis. And you have 3 or 4 degeneracy in the ground state, and there are no other ground states. And now you can deform this classical Potts chain to make it quantum. And this is one choice of M operator. M is just a tensor product of this 3 by 3 matrix, which is written in a tau diagonal basis. And here I take C to be just identity. And then if you deform the classical model, then you get this complicated Hamiltonian, and these parameters P and F are some complicated functions of these parameters alpha and R and theta here. And so the Hamiltonian is quite complicated, but you can still write down the ground states. And the ground states are, they get modified by R and theta here. And when you set theta to 0, then you recover some known previous results by Iemini and others. And this is one deformation, but you can also consider some other deformation. And the M operator looks a bit different. So here you have R squared, but here it's just one R on the diagonal. But here I take C operator to be this tensor product. So this K is just 3 by 3 matrix, which acts on the J's and J plus 1 sides. And using these M and Cj, you can deform the Hamiltonian this way. And then you get this kind of Hamiltonian, and it's no longer classical. You have a quantum term here. But still, you can write down the ground state in this way, and there are no other ground states. And this reproduces some other previous results. But these two are just examples, and you can actually construct infinitely many different examples. And you can also prove, in some cases, you can prove the existence of a gap above the ground states. Okay, so it's almost the time. But so far, I've been focusing on rather simple M operator, which is just a product of diagonal matrices. But you can consider more non-trivial M. And actually, you can construct more non-trivial M using some involved algebra called the Templey-Lieb algebra, which was discussed in the more static context. And this algebra is generated by these generators Bi, and they obey these relations. But this guy squares to itself, proportional to itself. So it's more like a projection operator, so it's not invertible. But you can consider some linear combination of this Ei and the identity. And then this is invertible unless Z is 0. And this is the inverse of M. And using this M operator, you can construct an invertible matrix product operator. But this is nothing but just a transfer matrix of 2D classical static model. And using this kind of M, you can construct frustration-free models. For instance, you can construct a 1D classical model by taking some appropriate D and Z here. Okay, it's almost the time, so let me summarize my talk. So today I focused on frustration-free type chain. And by starting from non-interacting and frustration-free type chain, you can construct interacting and frustration-free. stack chain. And here's the expression for the ground state, and it's basically a coherent state of Fermi operators. And you can also prove the spectral gap about the ground state. And using this kind of trick, you can also construct tons of examples of frustration-free models for power fermions for Potts chains. Okay, yeah, thank you for your attention.
If not, then let's take us together.